Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go through an exercise where we're going to check the boundedness and monotonic behavior of given sequences. And we're going to do this by looking at their nth term. And we're going to confirm our results by using a graphing utility. And in your case, this could be like a TI-84 to confirm our results. And boundedness and monotonic behaviors are important because in the next exercise, you will see that we're going to use these two properties to deduce something about the convergency of sequences. All right, let's hit the road. All right, let's start with part A. So we have an equals -2 over 3 to the power of n. And let's see what we can say about whether it's monotonic and bounded. So there are alternate ways to check the monotonic behavior. One is looking at an plus 1 minus an, so the difference between two consecutive terms. And if this is positive, then an is probably non-decreasing, or you can put equality sign here as well. And if this is less than or equal to 0, it's a non-increasing sequence. Okay, and another way to look at it is just checking the ratio of two consecutive terms of the sequence. So an plus 1 over an. Well, this is to be positive to start with, by the way, if you want to use this behavior. So if this is less than 1, if this is less than 1, that means the one before is less than the one. The one after is less than the one before, so an is non-increasing. And if this is greater than 1, an is non-decreasing. I hope I said it correct. Okay, so non-decreasing, non-increasing, non-increasing, and non-decreasing. Okay, so and you can also put the equality signs here, because you may perfectly have a constant sequence. Like all of the terms are constant, so you may have the monotonic behavior over there. So going back to this question, let's check which one is more applicable. I think this one is more applicable for this one because this one takes positive and negative values. So let's check the very first property. All right, so an plus 1 minus an is equal to -2/3 to the power of n plus 1 minus -2/3 to the power of n. So how can we decide if this is less than 0 or greater than 0? Well, because we have to prove this for all n. So, well, here, -2 over 3 to the power of n is a common factor because I know that I can decompose this as -2 over 3 to the n times -2 over 3 to the power of 1. So that's how we split this term. So this way, this term becomes a common factor, so I have -2 over 3, -1 coming into the parentheses. So this implies that this is equal to -2 over 3 to the power of n times this is adding up to -5/3. Okay, n is odd. Okay, so that means you're talking about the odd powers of a negative number. And that is negative, no matter what n is. And negative number times another negative number, which is -5 over 3, is going to take you to a positive number. So when n is odd, an plus 1 minus an is positive. Okay? When n is even, the behavior is different because this term is going to be positive always. And positive times a negative term is going to be negative. So we can't really conclude anything when n is even. I'll just write this first before I make my conclusion here. Okay, so it's essentially this term becomes positive for certain n's and then negative for certain n's. So there's no consistent behavior here. So we immediately conclude that an is not monotone. Okay, an is not monotone. In the next slide, we're going to check if an is bounded. And here we go. So we're going to try to find an upper bound and a lower bound. So one observation is that this term here is always less than 1 to the power of n, which is 1, and greater than -1 to the power of n, but for certain values it becomes -1. So essentially this term is going to be always greater than -1. So essentially I found two bounds. One is the lower bound. Going back to the description of the theorem, this one was referred as n. Okay, so let's go back here. So this is my n. And this upper bound is my m. So essentially, the sequence is bounded by 1 from above and then -1 from below. We can also represent this by an absolute value symbol. So an, essentially, the absolute value of an is less than 1. So we conclude that an is bounded. So in this example, we have the monotonic behavior. We don't have the monotonic behavior, but we have the boundedness behavior. And unfortunately, we can't use this theorem because this theorem is only valid when an is both bounded and monotonic. Okay, the sequence may still be convergent, but we can't use this result at least for the first sequence -2/3 to the power of n. So in the next step, let's check an equals cosine n over n. But before we jump into that, why don't we graph this this sequence here and see how the graph looks like. And here we go. So if we graph this function, as you see that it fluctuates up and down, up and down, up and down. So this doesn't have any monotonic behavior. It's not like increasing or decreasing consistently. But we know that the values of, or the terms of the sequence they are bounded by 1 from below and -1 from below, which essentially means that all of the dots that you see in this picture are located in the strip from -1 to 1. And another observation here is that even though we can't use the monotonic bounded monotonic behavior to deduce convergency, we still have the sequence convergent. As you see that it converges to 0. Even though it fluctuates all the way, so it fluctuates as you see, it fluctuates, but eventually the terms sort of converge to 0. So this is a very good example where you can't use the monotonicity of the sequence, but you can still deal with a convergent sequence. Right now, let's jump into an. But one more, in fact, quick observation that I want to point out is that if you have the terms of a sequence alternating between minus and plus, there you don't really observe any monotonic behavior. And this is implicitly the case in this description here, because cosine takes positive and negative values. Because if you graph cosine function, it's for certain values of n, it could be positive, negative, positive, negative. So what that means is cosine is also alternating its sign for certain values of n. So if you want to check the monotonic behavior here, probably you won't have 1, because when you write down, let's say an plus 1 over an, let's say in this case, that is cosine n plus 1 divided by n plus 1, all divided by cosine n over n. And I can flip the bottom over, so cosine n plus 1, n plus 1, n over cosine n. So here the deal is not this part, but the division of two cosines. So So you can use your calculator, in fact, right now. For certain values of n, this could be negative, and for certain values of n, this could be positive. Okay, so that's bad because we want an plus 1 over an to be positive to start with, and we check if this is less than 1 or greater than 1. So for certain n values, I'm going to show in the table of sample values, but you can also try that with your calculator. So there's no good pattern of this ratio to be less than 1 or greater than 1, but in the meantime, it is positive. So here's me graphing the values of cosine n over n. As you see that the values fluctuate from minus to plus, minus, plus, minus, plus, minus, plus, minus, plus, as you see. So that's not a monotonic behavior. And you can also see that from here. See, like, it decreases all the way and increases and decreases and increases, decreases and increases. So this is not a monotonic behavior. So now in the next slide, let's check if an is bounded. But before then, let's just put here that an is not monotonic. And to show it's bounded, I'm looking for an upper and lower bound. So, well, cosine is a function. This is something that we recall from trig or pre-calculus. Cosine values always fluctuate in between -1 and 1, no matter what the argument of cosine is. So I can put equality signs here, and I can just say that this cosine guy is always less than or equal to 1, so that I just keep the bottom as is. And this is also always greater than or equal to -1 over n. Okay. Well, these bounds are still depending on n. I need constants, not depending on n. Well, I know that 1 over n, no matter what, is going to be less than 1. I can put the equality sign here just for the case of n equals 1. And here, these guys are always greater than or equal to -1. So in this case, I have m. M is the upper bound, so m is here. N is the lower bound. As you see that I have upper and lower bounds, so I can just like deduce that an is bounded below and above, so it's bounded essentially. And I can also use the absolute value symbol here, since an is bounded below and above by 1 and -1 respectively. So I can just say that an, the absolute value of an, is less than or equal to 1 for all n. Okay, so going back to the analysis, an is bounded. That's what we showed. That's what we showed here. But an is not monotonic. So going back to this behavior here, this theorem, the description of the theorem here, that we can't really deduce anything about the convergency of the sequence by using these two properties, because this is a nice theorem, and once you have boundedness and monotonicity of the sequence, convergency is in your pocket. So I don't have this part, but this is not enough for me to conclude anything about the convergency. But don't get me wrong, because we just said that cosine n over n is a convergent sequence, even though it's not monotonic and it converges to 0. So these two examples are really nice in terms of not being able to use the theorem to deduce convergency. Okay. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.